So let's see. So we're doing this, right, Allison?
I think so.
Okay. I'm going to blame you if it doesn't work out. Okay, now, but you see why we might do this. Because if we do this, you notice what's going to happen. We're going to have a square on top, right? And the square of a square root, or the square root of a square, just goes away, right? But what is the nice thing that you'll have on the bottom? You have the difference of squares, right? And that'll look just like one of our thingies, right? So let's see. Let's see what we got. So we've got minus 19 to 0. Now, I'm going to go ahead and write it as two different radicals, okay? So I'll have square root 19 plus y squared on the top. And I'll have square root, and I'm going to call this 19 squared minus y squared dy on the bottom. There's no need to know what 19 squared is at this moment. Everett, is this making sense? I mean, you asked for it.
No, yeah.
Okay. All right, so here we go. So this is integral minus 19 to 0. Now, all we have on the top is 19 plus y. And on the bottom, we have square root 19 squared minus y squared dy. Now, I mean, if I was me, I might start looking at this and going, well, I can actually turn that into two integrals, can't I? So I can make that integral minus 19 to 0. 19 over square root 19 squared minus y squared dy plus integral minus 19 to 0 y over square root 19 squared minus y squared dy. Now, you know, the second one here, what is it that occurs to you in that second one?
You can use U substitution.
That's just a simple U substitution, isn't it? Because I've got a function and part of its derivative in there, right? So let's do that. So on this second one here, I'll just separate this out and do this. And I'm going to leave off the limits of integration here. Do I want to do that, or do I want to? You know what? I'm going to sub the whole thing. So let's do that. So we're going to say, let u. Now we're just doing this part right here right now, right? So we're going to say, let u be, and I think probably the best thing to do will be 19 squared minus y squared, right? And then du will be minus 2y dy. No, I don't have minus 2y dy. I just have y dy. So I'm going to multiply both sides by negative a half, right? So minus 1/2 du will be y dy. Excellent. That's all there. And then I might figure out what u of 0 and u of minus 19 are. Okay, so u of 0 is 19 squared. And u of minus 19 is 0. So what do I really have here? Then I have integral 0 to 19 squared. 1 over, do you want to do it that way? Or let's call it u to the minus 1/2. So I'll have minus 1/2 u to the minus 1/2 du. Okay? So we have minus 1/2 times 2, right? Because when we add 1 to minus 1/2, it's going to be positive 1/2. Flip that over and multiply. That's 2. And then we've got u to the 1/2. And that'll be evaluated from 0 to 19 squared. Okay, so that now is just going to be minus u to the 1/2, right? And if I put 0 in there, I'm getting 0. And if I put 19 squared in there, I'm getting 19, right? So this is just going to be, what is this going to be?
Negative 19.
Yeah, negative 19. Okay, so that takes care of that part. Okay? Now, we want to think about this other part right here. Okay, now the fun part. Integral minus 19 to 0, 19 over square root of 19 squared minus y squared dy. I think what I'm doing is I'm going over here and I'm saying, well, which thing do I have? Do I have x equals a sine theta, x equals a tangent theta, or x equals a secant theta? And I don't have to know, like right off the bat, because I can figure it out. I can just go, okay, well, if I have x equals a secant theta, and since I've got 19 squared in my brain, and that's just a y square, there's nothing in front of it, I don't have to worry about coefficients. I'm just thinking that a is 19, right? So if a is 19 sine theta, and I'm just going to run through them, see which one I'm going to do. Now I know it's not tangent, right? Because the thing I remember about tangent is that one's a plus, so I don't have to worry about that one. Now if that's true, then x over 19 would be sine theta. So that would put x here. That would put 19 here. And that would put 19 square minus x square here, right? So I believe that's what it's going to be. I think we've got it figured out here. Okay, so x is 19 sine theta. That means then that dx is 19 cosine theta d theta. And I should be using y's, shouldn't I? But that's all right. We'll just make all those y's into x's as we do this. Now, I also need to know, so I've got dx. I need to know what square root of 19 square minus x square is going to be, right? So that's going to be square root of 19 square minus, okay, now x is 19 sine theta, and that's squared. And so now I'm pulling a 19 out, right? So I've got square root 19 squared times 1 minus sine theta squared. But that is 19 cosine theta, right? Okay, so what do we got now? I'm not going to worry about limits of integration here. We'll substitute back on this one. So I've got 19. I've got dy, okay, or dx for us. That's 19 cosine theta d theta. And then I've got 19 cosine theta on the bottom, right? Are we all accounted for? Did we get everything? I think so. All right, well, the 19s and the cosines are going to go away nicely, aren't they? So we're just going to have 19 integral d theta. Okay, so that's going to be 19 theta plus any old constant. Okay, good. Well, but it's not theta that I want. It's x or y. So I'm going to say, okay, well then what's theta going to be?
Arc sine.
Yeah, very good. So theta is going to be inverse sine x over 19. Okay, so this whole thing then is going to be 19 inverse sine, and it's x over 19, but I'm going to call it y because we're going back up where we were, right? Okay, now, how do I evaluate this thing then? Okay, so I take that, 19 inverse sine y over 19, and I use these limits of integration, minus 19 to 0. Okay, so this is going to be 19 inverse sine 0 minus inverse sine minus 1, right? That's really horribly spaced. There. Okay, so I need to know something about the sine of inverse sine of 0. Let's see. So on that interval, let's think about where is the inverse sine defined. Inverse sine is defined on which quadrants? Here, and if you don't remember that, here, this is the easiest way to remember this. What does the sine function look like? Looks like that, right? Not 1 to 1. I need an interval where it is 1 to 1. Well, if I just eliminate that part, not only is it not 1 to 1, it's also, I don't have all of the values of the sine function, right? I've only got the positive ones. I need the negative ones. So we go back here like this. Now eliminate that part. Now we've got a representation of the sine function on an interval that gets all of the sine values, minus 1 to 1, and it is 1 to 1. What quadrants is that? Yeah, first and fourth. So that is right through there. Okay, so I need to figure out where is the sine 0, because this is inverse sine, right? Where is the sine 0 on that interval? 0. Good. So this then will be 19 times 0 minus, okay, then where is the sine negative 1? Well, now, but remember, that's true. The sine is negative 1 at 3 pi over 2. However, is the inverse sine defined at 3 pi over 2? Say no. It would be, what would we call it instead of 3 pi over 2? Yeah, negative pi over 2. Very good. Okay, so we've got 19 pi over 2 here. Okay, but that's not our answer, right? Because we had to combine it with the other part. So, in this gigantic mess that I have here, because I did a horrible job of organizing all this, okay, in all that mess, I've got this part that's 19 pi over 2 and that minus 19. Now, which one comes first? Yeah, the 19 pi over 2. That was the green one, right? Okay, good. So this answer then, if I didn't blow anything up to here, will be 19 pi over 2 minus 19. Okay? Was that the answer that was?
Yeah.
Good. Is everybody clear on the process? That's the whole thing. It's not necessarily getting the answer right. It's the process. Yes, ma'am?
I don't understand what you're doing with the triangle.
On the triangle.
Yes.
Oh, up, right up. Here. That part. Okay. So here's what we did. We went back in our brains and we said, okay, there are 3 possibilities. Those possibilities are x equals a sine theta, x equals a tangent theta, and x equals a secant theta. So what we did was we drew a triangle and we said, okay, I'm just going to start with the first one. X equals a sine theta. Now I know that because I've got a 19 square here, underneath that radical, that I'm counting on A being 19. Okay. So then I said, okay, I'm going for the first one. X equals A sine theta. If it doesn't work out, I'll move on to the next one. So when we did that, that put if X is 19 sine theta, that means that sine theta is X over 19, just dividing both sides by 19. But we know that sine theta is opposite over hypotenuse, right? So I looked at where I have theta. I put X on the opposite and 19 on the hypothesis, then used the hypotenuse. That's a new Greek god, hypothesis. And then I put, and then using the Pythagorean theorem, the Pythagorean theorem, it puts the square root of 19 squared minus x squared on that other side, and that's the form we were looking for. Does that make sense now? Is the triangle working out now for you?
And thank you so much. That actually helped.
Good. I'm glad.
So,
I'm glad.
because I was banging my head last night trying to figure that question out. Still got it wrong. Used the integral calculator. Still couldn't get it. And that, yeah. Anyway.
Head banging can work.
What's that?
Head banging can work. It can jog just the right thing loose. Okay, go ahead.
So it's the integral of 10 dx over secant x minus 1.
Okay, and are you still like looking for something that I can't do?
Oh, no.
Okay. Now, is the x minus 1 in parentheses?
No, sir.
It looks like that.
It looks like that.
I think if we were to multiply the top and bottom by secant x plus 1, what we wind up with is integral, I'm going to put the 10 out front, secant x plus 1 over secant square x minus 1 dx. Now the question is, does that help us? Well, I might run through my Pythagorean identities and see if there's a thing here. So I've got sine square x plus cosine square x equals 1. Now I want one that's got secant in it, so I'm probably going to divide both sides by cosine square, right? So what I'm going to have is tangent square x plus 1 equals secant square x. And what do you know? Tangent square x would be secant square x minus 1. Okay, so I can rewrite that guy up there as 10 integral secant x plus 1 over tangent square x dx. And I think, again, we can make two integrals out of it, can't we? So we have 10 integral secant x over tangent square x dx plus 10 over 10 times integral 1 over tangent square x dx. Okay, now, I don't know anything about tangent square. Do you know anything about tangent square? But I think we did this last time, didn't we? What did we do? Yeah, we just changed everything to sine and cosine, and that just made everything look a lot more familiar, right? Okay, so let's see. We've got 10. Secant is going to be 1 over cosine x over sine square x over cosine square x dx plus 10 integral 1 over sine square x over cosine square x dx. And so we have 10 integral. Now I'm going to invert and multiply, right? So we'll have 1 over cosine x times cosine square x over sine square x dx plus 10 times integral cosine square x over sine square x dx. Now, we have 10 integral cosine x, and right now we're rejoicing over sine square x dx, right? Very simple u substitution because derivative of sine is cosine. Oh, but our rejoicing stopped. And the room goes silent because we have sine square and cosine square.
The cosine over sine squared?
Yeah, I'm not. That one's fine.
Oh, okay. you're
Yeah,
asking-
I'm more worried about that second one. Cosine square over sine square.
Half angle? Well, oh, sorry, go. Half angle identity since they're both even?
Well, so we talked about that, didn't we? Yeah, go ahead.
I was thinking maybe splitting it into 1 minus sine squared is equal to cosine squared, so that you could have 1 minus sine squared over sine squared, and then you split that up. I don't know. That's
That's not a bad idea. To me, that actually seems like it would be a bit more simpler than making those two big fractions on the top and bottom when we do the half angle. So let's give that a try. Look, anytime I can go with a Pythagorean identity, I'm doing it. It's a lot nicer. So let's see. Let's do what we did last time. Let's just take the second one, and work on that individually, okay? So, because, I mean, like, there's not a question about the first one. So we've got 10 integral 1 minus sine square x over sine square x dx. So we've got 10 integral 1 over sine square x dx minus 10 integral dx, don't we? Because the sine squares are going to cancel. Now, okay, I think, what are we going to do now? I got a sine square on the bottom.
Isn't there like,
You could do a half angle identity.
I was gonna say like, just make like cosecant squared, because isn't that like.
Okay.
Oh,
Cosecant
yeah.
squared.
And then that makes so much more sense.
That's called learning by trial and error.
Oh, yeah.
10 cosecant square, integral cosecant square x minus, and 10 dx, that's just going to be x, right? Do I put a c yet? Say no.
No,
Why not?
it would look ugly.
Why no? Why don't I have to put a c yet? Because what?
We haven't done the other one.
Because of this integral right here?
We haven't done the other one.
There's too many integrals.
So that 10 integral cosecant square x dx has a built-in constant, right? Yeah. We are still yet to finish integrating, so we still have a constant to add. Does that make sense? All right. Now I could put it, and then I could say I have a second constant here, but when I add two constants together, what do I get?
2C.
I just get a constant, right? I got a C1 and a C2, put them together, I just still got a constant. I can just call it C. Okay. So, what's the integral of the cosecant square? Negative cotangent, okay. So we have minus 10 cotangent x minus x. Now I'm going to put my plus c, right? Okay, so there's the second one. The first one,
Is it 10x?
I was about to say.
Yeah, do we want to put parentheses or divide it, distribute?
oh, I'm sorry, I didn't put the 10. You are right. Very good.
You would have gotten that question wrong on the Pearson.
Should that be a 10C?
No.
No. Okay,
I mean, it could be.
could be,
See again.
but people would point and laugh if you did that. So,
Happens so many times.
Here we go.
I'd just stop here, honestly. I'd go take a break.
New quiz. Just take a break.
Yeah. Okay. So now 10 integral cosine x over sine square x dx. So I think what we're doing is we're going to say let u be sine x, then du is cosine x dx. So this whole thing then becomes integral, 10 integral, u to the minus 2 du, which then becomes minus 10 u to the minus 1 plus c, which becomes minus 10. I could write this 1 over sine theta, couldn't I? But should I? How else could I write it?
Cosecant.
Yeah, I could write it cosecant. Okay, now we're going to put the two pieces together, right? So we have our this part here and this part here to add together. So this whole thing then is going to become minus 10 cosecant x minus 10 cotangent x minus 10x plus some constant. Is this the answer that you guys got when you checked it?
Yes, sir.
Okay. I'm going to, so 2 cosine 4x. I'm just going to do this separately over here. Do a little scratch work. That just is so inconsistent. I'm not quite sure what my technique is supposed to be. 1 minus sine x. So, you're saying, what if we went square root 1 plus sine x on the top and bottom? Now we end up with 2 cosine 4x square root 1 plus sine x over square root 1 minus sine square x, right? But this whole thing turns out to be 2 cosine 4x square root 1 plus sine x over cosine x, right? And then a cosine eliminates. So we wind up with 2 cosine cube x square root 1 plus sine x. So did that help us? So we would have integral 5 pi over 6 to pi. We still have the 2. And we have cosine cube x square root 1 plus sine x dx. Did we gain an advantage there? So this would be 2 integral 5 pi over 6 to pi cosine x cosine square x square root 1 plus sine x dx, right? Now we have 2 integral 5 pi over 6 to pi cosine x 1 minus sine square x square root 1 plus sine x dx. Let's think about
I'm not here to see what.
1 plus sine square x, or 1 minus sine square x rather, is what I meant to say. Now, wouldn't that be 1 plus sine x, 1 minus sine x? And if I multiply that by 1 plus sine x to the 1/2, which is what the square root of 1 plus sine x is, then wouldn't that combine with the 1 plus sine x to make 1 plus sine x to the 3/2? So wouldn't I have 1 minus sine x times 1 plus sine x to the 3/2? I'd have that, wouldn't I? Okay, so did that take us anywhere? Well,
I was thinking you could do 1 plus sine x, because then it'll just be u to the 3/2, and then for the other sine x, you just find we're like, because if we have u is equal to 1 plus sine x would be equal to u minus 1, and so you have like, that's simple, and inside the square root is, that was what I said a minute ago.
yeah.
I realized it's a sine squared x.
Let's give that back. That's not what I heard you say a minute ago.
No,
So
that's
now-
the same thing, but with missing the step in between.
So let's give that a whack. That's good. Let's give that a whack. So everybody seeing the logic here? So let's let u be 1 plus sine x. Now, du is still cosine x, right? Okay, that's looking pretty good. But what about that 1 minus sine x?
Because you can just put like u equals 1 plus sine x, just solve it for sine x.
Good. So we have sine x equals u minus 1.
You just sub that and then it'd be
Yep.
2 minus u.
So 1 minus sine x would be 1 minus u minus 1, right?
You actually equals Paul.
I like 2 minus u better, yeah. Okay, now, what do we got? Can we substitute some of that mess in here? So we have 2 integral. Now we're making u substitutions, so we're killing the limits of integration. So the cosine x dx is just du, right? The 1 minus sine square x, well, we're down here now. That whole thing, what's left is down to this 1 minus sine x, 1 plus sine x 3/2, right? That 1 plus sine x to the 3/2 is u to the 3/2, right? And the 1 minus sine x you decided would be 2 minus u, right? Have we accommodated everything now? Is that everything accounted for here? I think so. I think we can integrate that. So we have 2 integral 2u to the 3/2 minus u to the 5/2, right? du. So what we got is, golly, where were we supposed to go from the start? We were supposed to integrate that thing. Well, we've got it down to here.
Can we not substitute in for u and then put our limits of integration into?
I think that's what I want to do. I would rather do that than substitute back, right? So I think what I want to do then is find out what u of 5 pi over 6 is, u of pi, and u of 5 pi over 6. Okay, so if u is 1 plus sine x, sine of pi is 0, plus 1 is 1. 5 pi over 6, so sine of 5 pi over 6, well, sine, we're in the second quadrant, right? Sine's positive in the second quadrant.
Oh, positive.
Yeah.
Oh.
So we've got 1 plus a half, so we got 3/2, right? So I'm gonna leave the rest of it to you guys, okay? All right, here we go. partial fractions. Here's the concept. If we're going like all the way back to like, I don't know, 10th grade math probably.
Can we stay there?
Hmm.
I was happy back then.
Yeah, no more chickens.
If I wanted to add those two things together, I would get a common denominator, right? So I'd multiply the top and bottom of this one here by whatever it lacks, and that would be x plus 3. And then I'd multiply top and bottom of this one by whatever it lacks, would be x minus 2. So we'd have combining numerators now, right? We have a common denominator, so we would combine numerators. X plus 3 plus 2 times x minus 2 over x plus 3, x minus 2, which would turn out to be x plus 3 plus 2x minus 4 over x plus 3, x minus 2. Now, if I was to combine all these terms, I'd have 3x minus 1 over, and then multiply that out, I'd have x squared plus x minus 6. Now, if I said to you, integrate that thing, you'd look at it and you'd say, well, I have a quadratic on the bottom, and I have a linear on the top. And so your first thought would be u sub. And you look at it and you go, darn, that's not going to do it, is it? Because I don't have a function and its derivative. But you do know that 3x minus 1 over x squared plus x minus 6 is equal to 1 over x minus 2 plus 2 over x plus 3. That's the exact same thing, isn't it? And when you're looking at that one, what are you going to wind up with? That one's a breeze, isn't it? Because you've got a function and its derivative there. So what do they both turn out to be? You can eyeball that.
Eyeballs must not be working.
Well, if u was x minus 2 in the first one, you'd have 1 over u du, wouldn't you? What would that be? Natural log. And if u was x plus 3 in the second one, you'd have 1 over u du, 2 over u du. 2 natural log. Okay, good. So
Eyeballs work.
this whole thing then would be natural log x minus 2 plus 2 natural log x plus 3 plus c. So if you started with this right here, it'd be really nice if you had a process where you could take that rational expression and take it apart so that it's something you could integrate. And that's called partial fraction decomposition. So we need a process for doing that, okay? What does that look like? Well, let's see. Suppose we have, I don't think I want that. Yeah, we'll do that. Yeah. Integral y over y plus 4 times 2y minus 1 dy. To tell you the truth, I'm not real sure I want that one, but
What's on the bottom?
y plus 4, 2y minus 1. Yeah, I don't think I really want that one to start. I'm not going to start with that one. So what I just said, forget it.
Nothing on the bottom.
I'm going to start with something else. I'm going to start with this. Yeah, let's do this. Integral 2x minus 1 over x squared minus x minus 6. Let's do that. Okay. Let's see. Let's go back over here. Here's something I can tell. That x squared plus x minus 6, I needed that to be factored, right? Because that's what gave me this x minus 2x plus 3. And going backwards, that's where we got it, right? That's where it came from, was having two separate fractions, one of them with an x plus 2 and one of them with an x minus 3. Okay, so I'm going to factor that. And we have x minus 3, x plus 2. Okay. So now, I'm just going to look at this by itself. Take away the integral for right now. I'm going to look at 2x minus 1 over x minus 3, x plus 2. And what we saw before was that we had two fractions, one of them with a denominator of x minus 3, and one of them with a denominator of x plus 2. Now, what was in the top? Well, some numbers, right? Now, something I'm going to notice is that both of these denominators are linear, not quadratic. So they're linear. So, and what I'm going to put in the top, and this is going to be a part of the process here, I'm going to put constant values in the numerators, no x's, because I've got linear denominators. If I had a quadratic denominator, an irreducible quadratic denominator, I'd have a linear numerator. So you go down 1 degree in the numerator, okay? Okay, now, well, okay, I still need to know what A and B are. Well, let's think about this. When you have a rational equation, how do you solve it? Aren't you just compelled to get rid of the fractions altogether? So you just multiply both sides by the lowest common denominator of all the fractions in the whole thing, right? So I'd have x minus 3, x plus 2. Okay, so let's see. On the left-hand side, it all cancels, doesn't it? The denominators cancel. So I just have 2x minus 1. On the right-hand side, I'm going to distribute that thing, and the x minus 3 is going to cancel in the first term. So I have a times x plus 2 plus, and in the second term, the x plus 2's cancel. So I have b times x minus 3. Now I'll go ahead and multiply those out, and I'll have 2x minus 1 equals ax plus 2a plus bx minus 3b. Now, that's an equation. The left side is equal to the right side. And on the left side, I have this 2x. And on the right side, I have ax plus bx. Well, I mean, if those two sides are equal, then those two x terms on the right have to equal 2x when they add together, don't they? They have to sum to 2x. Well, that also tells me that a plus b would have to be equal to 2. Because if they equal anything else, then if they add to anything else, then it's not, the left side's not equal to the right side, right? Now, I also see that I have some constants on the, a constant on the left, -1, and some constants on the right. So I also know that 2a minus 3b would have to be equal to -1. Everybody doing good so far? And now I have a system of equations. I could multiply, let's say we multiply equation 1 by 3 and add that to equation 2. Because that's going to give me 3a plus 3b equals 6, and 2a minus 3b equals -1. Add them together, and the b's go away, and I have 5a equal to 5, which tells me that a is equal to 1. Now, hopefully you're good with the elimination process of solving a system of equations at this point. Okay, so now, I know that a is 1. I know that a plus b is 2. So that tells me that b would have to also be equal to 1. Okay, so now, let's rewrite this integral. All right, so I'm going to have the integral of, now, a was 1, so that's 1 over x minus 3. B was 1, that's 1 over x plus 2 dx. I'm in the same boat, aren't I? These u substitutions are really simple at this point. U is x minus 3 in the first one. Du is just dx. U is x plus 2 in the second one. Du is just dx. So all I have is the natural log of x minus 3 plus the natural log of x plus 2 plus c. Now, how cool is that? Do you feel clever?
Is this another change your life type of integration?
I'm about to change your life.
He's gonna add not denominator.
That's right.
Yeah.
And we're going to make some huge systems of equations. Are you excited about that?
All the computer science texts are excited.
Yeah, Allison's going to write us a program that's going to do this for us.
I think the program is called like integral calculator.
Somebody already wrote it?
Yeah, there's like a principle in like computer science where you don't just you make things to save your sanity.
Yeah.
You know, I had a friend who was a networking major, and they were just allowed to like look up the answers to almost everything.
That sounds like a networking.
So what you're saying is that computer science is all about plagiarism.
I mean, we're not out here making our computers from
I
scratch.
challenge you to write binary code. Like,
Yeah, write a compiler. real
I can
quick.
put ones, zeros and ones all over the place. All right, here we go.
but can you integrate this?
Have you ever seen that T-shirt? There are only 10 kinds of people in the world: those who understand binary and those who don't.
You're very.
Yeah, I'm in the latter.
All of the nerds are laughing there. That's all.
Which is 2.
Now, we just threw a wrinkle into this thing.
29 at the top.
You ripped the blanket.
Here we go. What's that?
Is that a 29 at the top?
It is a 29 on the top. Yes, it is.
Is that an X squared bottom?
There's all kinds of x's on the bottom. Yeah, x minus 4 square, x squared plus 3 dx. Okay. Now, you remember in the last one, you remember the old days 5 minutes ago? When we had just a couple of nice linear factors? Well, this time we've got, I'm going to do this a little bit differently. So this time we have just a little more complicated here. So we have to remember some rules about this game that we're playing. And the first one we're going to see in that repeated linear factor. X minus 4 is linear, right? But it has multiplicity 2 in our denominator, right? It's repeated. So here's what you get to do. You get to have a term that just has an x minus 4, and it'll have a linear numerator. And then you get to have a term that has an x minus 4 squared. So every time you have a repeated factor, you have a term on the right that has that factor raised to the first power, then that factor raised to the second power, If it was cubed, there'd be another one with that factor raised to the third power. So you're going to have one for each successive power, starting from 1 up to whatever your exponent is on that factor, okay? And that would also have, because it's linear, it's a repeated linear factor, it also has a constant numerator. Okay, now, but you notice that x squared plus 3 won't factor into nice real roots, right? So that will be an irreducible quadratic denominator. And since that is an irreducible quadratic denominator, that will have a linear numerator. Okay, is everybody understanding what just happened? And how I got all those pieces. So now, those are basically the rules of the whole thing. I mean, it's not going to get, like, you don't have to remember more stuff than that about doing this. Okay, so now let's multiply both sides by our lowest common denominator. So that's going to be x minus 4 squared times x squared plus 3. Okay, on the left, denominator cancels. So we have x squared minus 29x plus 5. Now on the right, we distribute. In the first term, one of the x minus 4's cancel. So we have a times x minus 4 times x squared plus 3. In the second term, both of the x minus 4 squares cancel, so we have b times x squared plus 3. In the third term, the x squared plus 3's cancel, so I have cx plus d times x minus 4 squared. Now we get to multiply all this out. So we have x squared minus 29x plus 5 equals a. Now, I'm going to multiply x minus 4 by x squared plus 3. So I'm going to have x cubed minus 4x squared plus 3x minus 12. I can go ahead and multiply through by this b now. I have bx squared plus 3b. I'm going to need to multiply cx plus d by x minus 4 squared, so I'm probably going to need to multiply x minus 4 squared out first. So I'll have cx plus d times x squared minus 8x plus 16. Okay, now I can multiply through by a over here on the right. So I have x squared minus 29x plus 5 equals a x cubed minus 4a x squared plus 3ax minus 12a. Then I have plus bx squared plus 3b. Now we're going to multiply cx plus d by x squared minus 8x plus 16. Okay, now that just means that we take cx, multiply it through by everything, and then d and multiply it through by everything. So let's see what happens there. Okay, so we'll have plus cx cubed minus 8cx squared plus 16cx plus dx squared minus 8dx and then plus 16d. That's some stuff, isn't it? Let's make our system of equations. All right. On the right, I got a bunch of x cubes, don't I? What's my coefficient on x cubed on the left?
0.
Yeah. So what does that mean? Oops. That means that A plus C is going to equal 0, isn't it? I'm going to check my work here. What's going on here? I got that part right. Okay? Now, what about my x squares? Well, I have a minus 4ax squared. I have a bx squared. I have a minus 8cx squared. And I have a plus dx squared. So that means then that minus 4a plus b minus 8c plus d would be equal to what? 1. Good. All right. Now let's see. I've got some x terms. I've got 3ax. I've got 16cx, and I have minus 8dx. So I have 3a plus 16c minus 8d, and what's that equal to? Negative 29, yeah. Okay. And we have some constant terms. Looks like details are important on this topic. And maybe lots of opportunities for error. So let's see what we have here. We have minus 12a plus 3b plus 16d equals 5. That is a heck of a system of equations. That could take many pieces of paper to solve. Okay, however, we could do this.
Thank goodness. I thought he was going to say get to work.
Actually, when I was your age, it meant get to work. But we have our handy calculators. Here's what we're going to do. We're going to make an augmented matrix out of this thing. Now, an augmented matrix is just those equations. It's just a system of equations. And all I'm going to do is I'm going to write out the coefficients. It's just important that you know where these numbers came from, okay? I have A's, B's, C's, and D's. Those are my variables. And then I have the right side of the equation. The first equation, A plus C equals 0. Here's what's going to happen. The A's are going to go in the first column. The B's are going to go in the second column. That coefficient is 0. The C's are going to go in the third column. That coefficient is 1. The D's will go in the fourth column. That coefficient is 0. Then I have the augmented part of the matrix where the right side of the equation goes. And in that first equation, A plus C equals 0. That right side is 0. Now, is everybody seeing where those numbers came from? That first line there says A plus 0B plus C plus 0D equals 0, which is what that first equation says. Okay? Now let's go and do the rest of them. So the second one says minus 4A plus B minus 8C plus D equals 1. The third one says 3A plus 0B plus 16D C minus 8D equals minus 29. And the fourth one says minus 12A plus 3B plus 0C plus 16D equals 5. So is everybody good with that matrix right there? Now let me ask you something. If you had a matrix that didn't look like that, looked like this. 1, 0, 0, 0, and then some number over here. I don't know what it is. And then it said 0, 1, 0, 0, and then some other number over here. I don't know what it is right now. And then 0, 0, 1, 0, and then some other number here, and 0, 0, 0, 1, and another number here. What would that last matrix tell you?
A is equal to.
Yeah, A would be equal to whatever that number is there. B, C, D. We'd know them all, wouldn't we? This is called row echelon form. We want to turn this matrix, our first matrix, into that second one. Now, there is a process called applying elementary row operations that is analogous to manipulating a system of equations. You would have done that several years ago if you were taking this class, like I did that when I was your age. But because Texas Instruments came along and showed you some love, you are going to use your calculator to do this. So we're going to take this thing right here and figure out how to get Texas Instruments to solve this system of equations for us. So here we go. You're going to use a function on there that says matrix. And I don't remember if that's its own key or if it's above something. It's above something.
For mine.
Okay, so you're going to hit second matrix. First of all, you're going to hit second quit. Make sure you got a clean screen. So you'll hit second matrix. Now, what you're going to do first is you're going to edit a matrix. When you hit second matrix, you've got 3 headings up there, right? Don't you have like edit, calc, names or something like that?
Names, edit, math, GPS, CPLX.
Okay, you're making things difficult for me.
I got it. I'm different.
I don't even have one.
Is it different than-
So what does it say?
Names, math,
Names, math, edit. Okay, the first thing we need to do is edit a matrix. Now, this thing right, whenever you edit a matrix, you have to know what the dimensions of the matrix are. The dimensions are listed in the form rows by columns. Okay, so what are rows and what are columns? Well, you sit in rows. You guys are sitting in rows, right? So rows go this way. Columns hold your porch up. So columns go that way. Okay, so how many rows do I have? I have 1, 2, 3, 4 rows. And I have 1, 2, 3, 4, 5 columns. So up there at the top of the matrix, you're going to put 4, enter, 5, enter. Now what that should do is put you down in the body of the matrix. And you should have 4 rows and 5 columns to fill in. So you just start typing all those numbers in.
Manually, that's 4 by 4.
If you don't have one of these calculators, you can get. There are some really good apps. One of them is called GraphenCalc. GraphenCalc. That one is a really, really good TI-83 emulator. There's another one, and if you want to be, one of the cool kids, you're going to definitely get graphing calculator emulators on your phone. Another one that I use, it's making me update, don't even do that to me. Oh, come on now. Calc 84, and it looks just like a TI-84. And all the functions work the same. You can't use that on a test. You need one of these if you want to do it this way. If you have another kind of handheld calculator that you have a Casio here, I have one of those at home. It works great. I really like those.
How do you get into like?
Can't remember.
Because all I can figure out is like how to bring it up, but it just like you can do like.
Yeah.
Just, like, push
Yeah,
over
it works well, but I haven't done it in so long because everybody has these TI
It's just half the
calculators.
price.
Oh, I know. All right. Once you have all those typed in, here's what you're going to do next. You have edited a matrix. You've got it edited, okay? Now we need for it to do some math on that thing. So we're going to hit second quit. We need a blank screen. Okay? Then we're going to go back and hit second matrix again. Then we're going to go over to that. On that first one, we did edit, right? On this one, we need to do some math. So go over to that math menu and drop down until you find the thing that says RREF. It might be like B or something. Or is it B? RREF. Was it B?
Yeah.
Okay. So now, what should be on your screen now is just that, just RREF. Is that right? And then is it like an open thing like this? It wants to know, what do you want me to do a row echelon form for? Did you put yours in matrix A? Did you just do it in the first one? Then now hit second matrix again. Don't clear. Leave that RREF and that open bracket on the screen. Hit second matrix again. Now we're going to go to names. And then you're just going to hit 1. And what you should have now on your screen is RREF and then an A like that. Do you have that?
Can I take a picture of this?
You sure can.
And is this being recorded as well?
Yeah. Yeah. For posterity, yes. For people with nothing to do. Okay. Now, you should be able to hit enter and get your row echelon form. So now, let's do that. So now we should have 1, 0, 0, 0, and then a number over here. And please tell me what that number is. 1?
28, 25th. Well, it's like one negative.
I think it's 1.
I got
Just
sync
one?
error. Yeah, it's one. No, I'm kidding. I can't figure out how to use it. It's old.
Okay, then we should have 0, 1, 0, 0, and -5. Good. This is all going according to my evil plan. 0, 0, 1, 0. -1. 0, 0, 0, 1. And just trying to calculate it in my mind, I think it should be a 2. Knew I could do it. All right, so good. What did we just find out? Well, let's go back over here. I'm going to take all this and we'll put it on another screen. All right, we see all that? So what we just found, oh, wait, and I need something else. I need this.
Would a 1991 calculator do this, do you know?
A 1991 calculator?
Yeah.
I don't know what that is.
Like a calculator from 1991. It's a TI-85, so I assume.
Oh, it'll do it. Yeah, 85 will do it, but I have absolutely no idea how.
Okay, gotcha. So just some Googling.
Yeah. If you were cool, you'd buy a new calculator.
Oh, yeah, true. I were a cool kid.
Actually, I think the cool kids do it by hand. Actually, they use a abacus.
Actually, I think the cool kids make so many mistakes doing it.
Maybe that's what I should do. I should just hand out an abacus for the test. All right. So what do we have right now? We're gonna do an integral now, and this integral will be our value of a 1 over x minus 4, because that's what it was, right? Plus our value of b, that was negative 5 over x minus 4 squared. Plus our value of c, that's negative 1x, plus d, that's 2, over x squared plus 3. So that now is what we'll integrate. How's everybody doing? All right, so let's see. I think I'm going to turn this into 3 separate integrals. So this will be the integral of 1 over x minus 4 dx minus the integral, I might call this minus 5, integral 1 over x minus 4 square dx plus integral minus x plus 2 over x squared plus 3 dx. Okay, so in the first one, I think that's just going to be an easy natural log, isn't it? So that's going to be natural log, absolute value, x minus 4. Now in the second one, I think I'm going to do a u substitution. So I'm going to do that separately over here. So I'll have integral minus 5 times the integral of 1 over x minus 4 squared dx. All right, so I think I'm going to let u be x minus 4. Then du will be dx. So this thing is minus 5. Integral u to the minus 2 du, which will be 5u to the minus 1 plus c. So 5 over u plus c, or 5 over x minus 4 plus c. That wasn't too bad. So working on this now, I've got minus 5 over x minus 4. Now, I think I'm going to split this up into 2 integrals. Do you guys think? I'll have integral minus x over x squared plus 3 dx plus 2 integral 1 over x squared plus 3 dx. Okay, I think I'll work on now that next one, because you know that minus x squared plus 3 over dx, that's a simple u substitution again, isn't it? So what are we going to do? I think we're going to, all right, so we've got integral minus x over x squared plus 3 dx. So let's see. I'm going to let u be equal to, I think, x squared plus 3. Then du will be 2x dx. I don't want 2x dx. I want minus x dx. So I think I'll go minus a half on both sides. So minus 1/2 du is going to be equal to minus x dx. Okay, good. So now I'm ready. I'm ready to go minus 1/2 1 over u du. So we have minus 1/2 natural log absolute value of u plus c. So we have minus 1/2 natural log x squared plus 3 plus c. Is that what everybody got?
For your second one, is it minus 5 over x minus 4, or is it plus 5 over x minus 4? How many negative signs do you have? You've got-
I took that negative sign right there with me. I took that sign with me.
Yeah, and then when you divide it by your exponent of -1, you got another negative, and then.
Oh, yeah, so it should be plus, shouldn't it? Yeah, you're right. So that should be plus right there. Right there, right?
I think so.
Yeah, good call. So 5 over x minus 4. Then we have minus 1/2 natural log absolute value x squared plus 3. And let's talk about that plus sign for a second. So that's one reason why. Normally what I do, and I didn't do it this time, and I should have made that a plus right from the start. If I was going to carry that minus 5 with me, I think it's a lot better so you don't have to deal with all those negatives running around. Make that a plus right from the start. So instead of where I've got that yellow highlighter there on the minus, that should have been a plus, and then it should have been a minus 5 over x minus 4. So that when you go to do something separately and bring it back, you don't have another negative to deal with. Okay, good. And then plus, okay, now let's see. 2 over x squared plus 3 dx. That is pretty interesting, isn't it? What are you guys thinking? What are you thinking?
Is that like this might be too complex, but arctan?
I think that's what it is. Let's see if we can verify that. We don't have to guess that anymore, do we? If we let x equal a tangent theta. Okay, and it looks to me like a would be the square root of 3. Okay, then that means that tangent theta would be x over the square root of 3. Now, tangent is opposite over adjacent, right? So I'd have opposite x over adjacent square root of 3. And this side here would be square root x squared plus 3, wouldn't it? So yeah, I think we are in good shape here to call that a tangent. So let's see. This integral then, I'll bring the 2 out front. 1 over x squared plus 3 dx. So we let x be, so x is equal to square root 3 tangent theta. So dx, let's see, what would dx be?
Root 3 secant squared.
Yeah. D theta. And square root x squared plus 3. Oh, wait a second. I don't have square root of x squared plus 3. I have x squared plus 3, don't I? Is that a problem?
No, because you just substitute it into that equation and then it becomes secant squared.
Well, so let's give that a try. So x is square root of 3 tangent squared, right? So we have, I'm gonna have to, gets cramped, doesn't it? How much paper are you guys going through today?
Trees.
Trees? All right, so let's see. We have x squared plus 3. That's going to be square root of 3 tangent theta square plus 3, right? So that's going to be 3 tangent square theta plus 3. That'll be 3 tangent square theta plus 1. And we decided earlier that that would be 3 secant square theta, right? Okay, so now, what are all of our parts? Now, I know what you're thinking. You're thinking, you know what, I could have looked this one up. And you're right, you could have. But this is just more practice with our trig substitutions, okay? So all of our parts are, so we want 2 integral. Okay, so 1 over 3 secant square theta, right? That's what x squared plus 3 is. And then dx is square root of 3 secant square theta. D theta. So what do I wind up with? I wind up with 2 integral square root of 3, 1 over square root of 3 d theta. But that's just 2 over root 3 theta plus c, right? And theta will be inverse tangent of x over the square root of 3. So this whole thing, boy, it got tiny.
Now do this 10 times in an hour.
Yeah. Also, you're like on the verge of like having a breakdown.
Yeah, also you can't talk.
And don't worry, the test problems won't be anywhere near this simple. All right, so this will be,
Sounds like that's just more practice.
is this going to be, 2 over root 3, yeah.
Why do you call it tan negative 1 instead of arctangent? You just prefer writing it that way?
Because it reminds me that it's an inverse. I always think of it as an inverse of the tangent function. Yeah.
Do you want to write out arc?
I prefer arctan so the negative 1 doesn't catch me so.
Yeah,
Yeah, because I could think of
that's what I
negative
do.
one as like tan x parentheses everything.
Yeah, especially if you're entering it
Never
into
had
years.
that problem.
Why?
Well, we're not all perfect like you, Lily, okay?
No, I have no problem with it, but I love the feeling.
You first.
Yeah.
I will say I'm lazy, so I can just do it first.
I also think arctan sounds so cool. Like imagine, lasers and stuff. I'm shooting a large scale.
You're shooting a mathematical
Yeah.
function.
That's all.
I think we got that right. Any questions about any of that?
It's fine.
That makes sense.
Now, let's go back over what we did.
Wow.
What in the world was this problem to begin with? Well, it was a rational function, right? That's a rational function that we couldn't integrate just looking at it like as a U substitution. So what do? We utilized our partial fraction decomposition skills, and we created a matrix that we were able to solve using our calculator. So that'll go quick now. That's good. Then we turned that into a bunch of terms. So integral of a sum, which can be turned into a sum of integrals. And we did that. And then integrated each piece bit by bit. And we got the opportunity to do a trig substitution along the way.
We were blessed to
Yeah,
use
the
our
flavor.
trick function. Thank you, Professor, for letting us use it.
Hey, look. You know, anytime you're good, I'll let you do good things.